Hi, I'm Ryan and I am a RIS intern and I will be presenting my work called the Sparse Attention Transfer for Geometric Foundation Models done at AirLab. So here is some of the motivation and background. So recently there's been this upsurge in popularity of geometric foundation models. What these models do currently is they take some set of RGB images and then they output the point cloud, either the depths, sometimes poses, sometimes all of them together, of those images, allowing you to create a 3D reconstruction of the scene. Some of these benefits is that these geometric foundation models are completely learned. They have these transformer layers, and then they get fed terabytes of 3D reconstruction data, and then using deep learning, it learns these 3D reconstruction. So some of the benefits of this formulation is that because it is learned, it has more semantic meaning than traditional SLAM methods. For example, it probably is more robust under fewer view counts, lighting, etc., maybe missing correspondences, compared to the classical methods such as SLAM, where it requires certain things, certain hand-engineered features, sometimes it fails. However, there's a problem currently with these foundation models is that you can't really deploy them in real time because the cost in the transformer layer is quadratic based on image count. So let's go a little bit deeper into this. So most geometric foundation models use Dino as an encoder. So Dino is a 14 by 14 patch size, and using 518 by 518 images, each image is around 1400 patch tokens. And when each token compares itself with every other token in every single view, this is O of n squared operation. So you can see how this starts to rack up. So at 512 views, you have roughly 700,000 tokens, and then you start squaring that, you all of a sudden have 5 times 10 to the power of 11 token pairs. So even on a H100 GPU, you can see this starts to grow quadratically, starting from 3 seconds at 128, all the way to 50 seconds at 512 views. So if you think of it as maybe you have a 30 FPS camera, and then roughly around 20 seconds later of content, it starts taking 50 seconds to get anything of output from the geometric foundation model, they start to become a little bit questionable in real-time usage, say putting it on a robot to help reconstruct. So our goal is to try to accelerate this. So obviously, what has already been done to accelerate it? Well, there's been many works such as FastVGGT, AVGT, and COMI, where they basically say a lot of the tokens are similar. Why don't we start merging them in blocks? These are all training-free methods, and basically it takes a 2x2 or 4x4 block and then says most of the patches are very similar and redundant. We can start merging them. And these are all, I would say, coarse methods that are applied after training. However, there's this other regime that LLM, since they also use attention and want long context, that seems to be getting better sparsity and is trainable. This is what we call sparse attention. It's used by DeepSeek, all these sort of efficient models, Kimi, Mimo, all those kind of models use this sort of sparse attention to combat this O of n squared attention problem. So what sparse attention is I can give one example on how DeepSeek uses it, is that instead of each query attending to every token in every view, each query only attends to the top 1024 tokens for that query. So now how do we decide the top 1024 without going through the O of n squared expensive operation? Well, we have to train some sort of router or indexer to calculate it, and this indexer should be much faster than dense attention. So our work is basically seeing if using these sparse attention techniques that LLMs use, and if we can transfer it to these geometric foundation models and be successful with reducing it and increasing a very high amount of sparsity and reducing that quadratic time complexity to make deployment of these geometric foundation models tenable. So let's do some analysis. So looking at the attention heads, we find that a lot of the attention heads of these geometric foundation models are redundant. So we will take the stable rank of the attention matrix produced by the heads and then calculate it. We find that a lot of them, the stable rank is extremely low, which means that a lot of it can be reduced. Or maybe some of the heads themselves are quite redundant. And then we see that the kernel, when we try to select 24 heads, 1024 top k from each query, there's a little bit of a weird problem. So you would think that the average time complexity is linear. It's O of 1024 times n, which should be faster than O of n squared, where n is very large number, like 700,000. However, it turns out naively applying it is actually slower. This is because the 1024 selection from each query is fine-grained, which means that we select 1024 across this KV head and are forced to gather for each KV head. We must gather the 1024, causing the kernel to be memory bound and not compute bound. And it turns out gathering 24 times top 1024 for each query token is slower than the dense attention. So how do we fix this for the geometric foundation model? Well, we will turn to what LLMs use, and that's grouped query attention. So instead of having 24 KVs, we're going to aim for having around 3 KV heads. So this can be done and supported by the fact that a lot of the attention heads seem to have a very low rank. So it seems tenable to reduce the amount of KV heads to maybe 3. So now we're into the main method. So as mentioned before, we have this geometric foundation model. We use map anything for this intern project, and then the map anything takes in the images, runs it through a transformer encoder called Dino, and then runs it through these global attention layers. So we will focus on the global attention layers, as that's the most expensive part of the component, and it's O of n squared. So we first start, as mentioned before, with the grouped query attention. We transfer this attention into grouped query by distilling the attention residuals from the original map anything model and then training it on a big data set. This reduces the KV heads from 24 to 3, greatly increasing our fine-grained sparse attention kernel as it reduces the number of gathers in the top K operation. Then we have to train a lightning indexer. This lightning indexer will score each of the tokens and produce a predicted coarse attention map that basically says, I think this is how much each token will attend to each other, and then we will take the top K of that. Once we have the top K of that, we feed it into our grouped query attention and perform this top K sparse attention. So to do this, in this intern project, we had to make quite a few Triton kernels for the training and the inference. To train the lightning indexer, we had to do a KL supervision with KL divergence of the attention distribution. And then at the end, we combine these components of our distilled group query attention plus our lightning indexer and then fine tune an end-to-end map anything on our data sets for training. However, that's still not the end of the story, because it turns out LLMs use quite a lot of heads and quite a big head dimension. So that lightning indexer, which I kind of glossed over in the previous section, is fast because it down projects the number of heads and the head dimension. That's how the lightning indexer in DeepSeek is so much faster. In geometric foundation models, on the other hand, we use not too many head dimension or number of heads. The lightning indexer is only around 2x faster than the dense attention, which at longer views still shows a very big quadratic trend. So we need to fix this. So we introduce another routing algorithm for the lightning indexer. So instead of scoring every single token with our lightning indexer, we're going to instead pool this image into blocks, which is similar to what previous methods have done, and then use the blocks to produce a candidate size. This candidate size can be much greater than 1024, and it can be performed much faster because we are pooling a lot of the patch tokens. However, the difference, which makes our method still fine-grained, is that we can use the lightning indexer's results then to rank each of the candidate tokens to get a fine-grained KV. So what we are doing is reducing the pool of top K tokens that are possible by using these coarse methods, but then at the second stage, still ranking them so that they are fine-grained. And then we implement some kernels to do this, such as radix top K. We have to keep in mind these kernel practices of tiling and shortlisting, sharing, all of those things. And upon implementation in Triton, we see we can reduce on 512 views the dense attention, which was 600 milliseconds per global attention, to 24 seconds, which is a huge reduction in speed. So here are some of the results. So we see that on 512 views, the map anything lightning, which is our formulation and method, is around 6.8 times faster on 512 views. Of course, this factor is not as large as we see here because map anything composes of an encoder, some local layers. Not everything is a global layer, so we need to keep that in mind. However, 6.8 times faster is still a much larger increase. And we see that compared to fast VGGT, map anything, fast VGGT, and the map anything lightning, fast VGGT is pretty slow, still exhibiting quadratic trends, as it basically only subsamples the tokens, reducing the sparsity to around 75%, versus our method, which takes a fixed 1024 per the 500 views, is much, much higher sparsity. And this method exhibits linear trends compared to map anything and fast VGT, which look quadratic. Then we see performance. Since we made such big speed improvements, now obviously we try to keep matching performance, which is not possible at the moment, but we see that based on some of the reconstruction metrics, that we are in line between map anything and VGT. VGT is a full attention VGT, and we are performing better than it with our sparse attention formulation of map anything. However, which I will note further in the limitations, we see that currently there is a decline in the performance of the sparse attention on more views, and we will address that further. Here are some qualitative results. You can see that on the E3D, tartan air, certain data sets, that our reconstruction looks pretty good compared to the ground truths and the dense map anything using our sparse method. So now we go into the limitations. So as mentioned before, on much longer views and larger scene extents. So importantly, tartan air is very large scene, and the model on bigger scene extents seem to struggle, especially on the pose part, and increasing this top K budget that we allocate per query token does not exactly help recovery, which seems to be a problem. One fix that we are thinking of implementing is that the lightning indexer currently decides this one query token should attend to this top KV for all the heads. If we can somehow make it so that this lightning indexer can predict for each head, this query token has its own 1024, because some analysis has shown that each head's for the same query token likes to attend to different things per head. So maybe we do an each query head top K instead of an each query top K for more fine-grained attention. Another problem was that the multi-headed to group-headed transfer had some accuracy reductions. So this transfer is not preserving the original performance as well as we hoped, especially on higher view counts. So one of the ways we are thinking of trying out is to instead use an analytical method to transfer the multi-headed attention, the grouped query attention. This analytical method will use singular value decomposition to learn a low rank matrix approximation of the MHA to GQA, which if you think about it, is what MHA to GQA is doing with the optimization goal of minimizing the logit error. And then finally, some next steps is seeing that certain layers we found for the global layers are more important than others. So using these sort of tricks of the per head or per group sort of top Ks should be maybe judiciously applied to the more important heads that require these sort of things, while certain heads are fine with just having this traditional top K that we designed, and then allocating it properly so that we can increase our reconstruction metrics while still maintaining the speed that our work goal is on.